Good day, everyone. Let me thank you all for coming here today and watching this video about a remarkable case that we were involved in a few years ago. My name is Yury Kolotovichev, the Assistant Lecturer of the Structural Mechanics Department of Moscow State University of Civil Engineering. Today, I'd like to talk to you about the approach taken to remove the uncertainties in the Beryozovskaya grass restoration with state-of-the-art monitoring and computer simulation technologies. I will make a primary focus on improving safety with automated monitoring data. Let me start from some general information on Beryozovskaya grass. It is a significant power plant located in the northwestern part of the Krasnoyarsk territory of Russia. Grass comprises 3 power units. The construction of the 3rd power unit shown in this picture was completed in 2015. The main building has been erected as a braced frame steel structure. 2 columns types were implemented. Its welded sections are shown below. On February 1st, 2016, an intense fire accidentally broke out in the boiler room of the 3rd power unit. Many people and vehicles were involved in the 6-hour extinguishing. Finally, the fire was localized and it did not affect units 1 and 2. Fortunately, no one was killed or injured, but the boiler room of power unit number 3 turned out to be completely disabled. The fire severely damaged the structures. In the following pictures, you can see extensive collapses of the load-bearing elements, envelopes, and parts of engineering systems. The massive boiler fell from the suspension holding it, leaned on the columns, and took on the load of the collapsed roof. As a result, a large amount of debris was accumulated in this area. This is a view of the collapsed boiler suspension approximately from this point. In September 2016, the owner approved an investment project for the rehabilitation of the 3rd power unit. The dismantling of damaged elements became the first necessary phase of this project. These 2 main problems heavily complicated the dismantling works. Many independent organizations together have performed services to evaluate the performance of the structure, and my talk will be limited by the first mentioned service, the automatic structural health monitoring system. The unpredictable internal forces for distribution caused primary concern during dismantling operations and debris removal. There could be not sufficient confidence in the results of the conventional structural analysis due to uncertainties in the damaged frame structures and the actual applied loads. There were unpredictable risks of sudden collapse due to the strength or buckling failure or the movement of debris. The instrumentation was concentrated at 4 elevations within the boiler room to compromise the ease of system maintenance and the quality of the data received. The number of sensors and their types are shown in this slide. This in the middle is how instrumentation was aligned in a particular column section. The strain gauges were installed on the column flanges by arc welding and covered with L-shaped profile to protect against mechanical damage. The tiltmeter were tightly attached to the plates welded on the columns and covered with enclosures. The sensors were connected to the automated data acquisition equipment distributed throughout the boiler room. Access to the monitoring data was provided via local and remote workstations. In the left part of this slide, you can see the layout of structural health monitoring system we launched in April 2017. And in the right position, there is a complete monitoring workflow. The finite element model of the damaged building was being updated periodically during the next 18 months, when the active phase of the dismantling works was held. The updating took into account the accumulated monitoring data to confirm that performing restoration work is safe enough. To obtain the required monitoring results in an automated way, dedicated software has been deployed on site. We put a lot of effort into providing owner and contractor staff with intuitive and self-explanatory information about structural performance in every single moment with easy access to historical data. That is why we augmented the system with many new features listed to the left: the instrumentation database, the database of structural elements, different procedures for processing raw measurement data, representation in form of time series plots or color indicators on the 3D model. Since the accumulated strain in the monitoring elements in the reference time is unknown, the finite element model of the frame structure in the damaged state has been developed by Moscow University of Civil Engineering staff. The damaged state was determined as close as possible to the building at the beginning of the strain monitoring in April 2017. The reference values of the internal forces obtained as a result of the simulation were later used to calculate the forces acting at an arbitrary measurement time. The approach that has been chosen to evaluate internal forces and stresses is shown in this slide. It is based on well-known and straightforward assumptions like the Euler-Bernoulli plane section hypothesis and the decayed geometry consideration. So I will skip it now and will not cover it in detail to save your time. The calculations of column parameters were entirely automated by deployed monitoring software. The customer received monitoring reports very handy, including diagrams of applied internal forces to the left and peak stresses to the right. The described technique of stress evaluation has helped identify and prevent an emergency that could arise in the section of one of the monitoring columns. In April 2017, the stress sigma 4, this green line, derived from continuous strain measurements, exceeded the warning level that was not predicted by structural modeling. Conjugated structural elements were strengthened and supplemental survey was established. The stress state finally stabilized. Further analysis of survey results and tilt monitoring data showed that the region of unpredicted column bending highly likely was the four-column cell twisting that could be raised by the lack of structural joints with collapsed boiler room parts. The last significant point of my talk is tilt meter measurement analysis. Processing the tilt data in time series plots is mostly inconclusive from an engineering perspective. It often doesn't allow us to see the overall picture of the column movements. To overcome this drawback, we developed a software module that created a graphical representation, trajectory maps, of the column angular movements during the arbitrary period to increase the clarity of the data. So let these pictures speak for themselves. A typical example that frequently occurred during the dismantling process may be seen in this slide. The peak-to-peak displacement of three shown columns are comparable, but only the last one clearly identifies the hazardous situation that must be alerted immediately. An abrupt movement used to be the first sign of potential progressive collapse. Plotting these maps for all columns in particular elevation provided a clear picture of frame structure movement in the rehabilitation process. Finally, I'd like to recap the main points of my talk. The monitoring system is really a preferable way to study the actual structural behavior with high uncertainties. Moreover, it gives an engineer feedback that is not comparable to computer simulation, which greatly simplifies reality. As I tried to illustrate in my presentation, the structural health monitoring system with dedicated software significantly improved personnel safety involved in the accident recovery. We proposed the automated stress and internal forces monitoring technique based on strain gauges data, and finally we suggested handling tilt methods data with plotting trajectory maps. We gratefully acknowledge the existence of all organizations mentioned in this slide. That brings me to the end of my presentation. Thank you for watching and listening. I hope I have made myself clear. Have a nice day.